Hello everyone, this is the first video in the Maxwell's equation series. If you have been struggling with Maxwell's equations in your electromagnetism course, this video will help you understand them better. James Clerk Maxwell, a Scottish physicist, came up with 4 distinct equations that basically served as the starting point in laying the foundation of electromagnetism. In this video, I'm going to focus only on the first equation. There were actually 2 other people who contributed to the creation of this first equation. And Maxwell, who was born last among the 3, followed the 2 other people's work and ultimately established it. So it was a timeless teamwork. But sadly for them, this equation ended up being named with a different guy's name, Gauss's law. You probably know Gauss. I'll explain the reason for this at the end, as it's not a big deal to us. It's unfortunate for them, but at least they have their names associated with other laws, so it's fine. We don't have to feel too bad. Okay, so everything started with this guy, Charles-Augustin de Coulomb, a French physicist, did an experiment observing and analyzing the electrical interaction between 2 charged balls. This led to the discovery of the famous electrical force equation, as shown here. I'll make another video about this experiment in the future, but for now, just know that scientists now know about this equation, okay? Around 50 years later, Michael Faraday, an English physicist, constructed what is now known as the Faraday cage. Using this cage, he demonstrated something interesting to the public. A charged object was placed outside the cage. When a person stood inside the cage, with only their head sticking out, their hair rose and pointed toward the charged object. But once the person was fully inside the cage, their hair settled down and no longer responded to the electrical force. Faraday believed that this phenomenon indicated that the force inside the cage somehow got cancelled and disappeared. But how would that cancellation work? He recalled the iron filings that respond to magnets. You've probably done this experiment at school or seen it online, right? Between the N and S poles, the iron filings align, forming paths that connects the 2 poles, and this is an actual picture, indicating the presence of a magnetic flow. And between 2 N poles or 2 S poles, the filings are separated, and that's an actual picture. As if the magnetic flow in the middle is cancelled out. Faraday thought that there's an invisible electric flow just like the invisible magnetic flow, and he called them lines of forces, which became the first term used to describe what we now know as the electric field. So using this concept of lines of forces, the electric field, he was able to explain why there are no electrical effects in particular regions when charges are present. The problem was he wasn't good at math. So he couldn't come up with any math equations to establish this concept. As far as I know, many scientists at the time ignored most of his hypotheses because he lacked mathematical knowledge. But there was one young physicist who respected him and supported his idea, and his name was James Clerk Maxwell. He wanted to prove that Faraday's idea was right. In my personal opinion, Maxwell valued Faraday for his experiment, believing that despite his weakness in math, his experimental work was more impressive than that of any other scientists. So let's see what Maxwell accomplished. First, he compared the electric force with the gravitational force. They look similar, right? When discussing gravitational force between 2 objects, if we, for example, focus on the perspective of the second object with M2, we can express the force that the second object M2 is receiving as F1 equals M2A1. By the way, don't confuse. I didn't mean A1 is the acceleration of the first object. A1 is the acceleration of the second object, but it's just the acceleration is caused by the first object, okay? It's still the second object's acceleration that I'm showing here. Anyway, for the electric force, we have charges instead of masses. So wouldn't it be proper to write Q times something? So this is how the electric field equation is derived. It's just the rest part. And if you think about it, it makes sense. If the electric field equation doesn't include the information about the second charge, Q2, this is like we're only talking about the Q1. So this electric field is caused by Q1. It belongs to Q1. As a generic form, let's just replace Q1 with Q, just like that. So, okay. We have an expression for the electric field, but this expression only talks about a single charge. How can we study the electric field when many charges are present? What Maxwell did was he carried out an intensive investigation on the electric field equation. Suppose we have a charge that emits electric fields in all directions. Actually, for simplicity, let's just talk about one line of the electric field for now, okay? Let's try to move the 4 pi r squared to the other side. Now the right-hand side is constant, but the left-hand side has a variable r. How can the left-hand side value change when the right-hand side stays constant? Actually, we shouldn't forget that the electric field depends on r. So it's like we have two variables that will work out a way to keep the right-hand side constant. So it's all good. Now, we have two vectors here, right? To multiply these two vectors, we must use dot product, also called the scalar product. Scalar product should give a scalar. And the right-hand side is scalar, right? As you can see. So everything makes sense so far. Now, is this area pi r squared? No, it was 4 pi r squared. So let's change that. It doesn't have to look exactly spherical. What I mean is, by turning this into an integral form, we can have an arbitrary shape instead, as long as it's three-dimensional. But again, just for simplicity, let's keep it spherical, okay? And by the way, since this is a closed surface area, we should write this integral like this. This means closed surface, right? Now, we always have to keep track of whether our derivation is correct so far. Do you agree? We can see that for this integration, we just gotta look at the entrance and the exit regions where the electric fields are not zero. So only these terms are surviving. But you know, these areas' normal vectors should look like these, since they are along the radial direction. So in the area's perspective, at the bottom, the electric field is entering in, and at the top, the electric field is exiting out. This means they will cancel each other and give us 0. But the right-hand side isn't 0. Does this integral make sense? I don't think so. Why don't we try to move this sphere down a little bit? Is it non-zero? No, this gives the same result. Okay, let's move this further down. How about now? Now the charge is inside the sphere. We just enclosed it. Didn't you notice anything? We now only have the electric field that is exiting. So the left-hand side does not cancel out anymore, so it has some value. This makes sense because the sphere does now have a charge in it, so the Q on the right-hand side. This integration should be correct if we make sure to enclose the charge. Or we can say that this integration only considers the electric field emitted from enclosed charges. Now, lastly, let's generalize this equation. If we have many charges, I'll use the capital Q, does this equation still work? So as you can see here, we have 4 charges inside. The integral will tell us that there are 4 electric field lines exiting, and there are 4 Qs in total that are enclosed. So 4 lines, 4 Qs. It's consistent. This is some cool math. What if we have one negative charge included in this region? We know that the negative charge should have its electric field pointing inward, since if this Q is negative, we will have the opposite direction. The integral will tell us that there are 4 lines going out and 1 line going in, right? So 3 lines going out in total. And what is our total Q enclosed? 4 plus Qs and 1 minus Q, so 3 Qs. 3 lines out and 3 Q enclosed. Everything makes sense. So if we integrate all the electric field coming out of the enclosed region, we can know the total charge in there. And of course, charges don't emit electric field in just one direction, but in all directions, right? This was just a simplified version, you remember? But it doesn't matter. That's just gonna be a multiple of our result. If we said that each charge emits 5 electric field lines instead, we would have gotten 15 field lines coming out in the end. So still indicating 3 Qs. And that multiple probably has something to do with this epsilon naught that we're dividing with. So I'll show you an example. Here I said that each charge emits 9 electric field lines, okay? Someone could ask, why do they all have to emit 9 lines? Some could have 18 lines. No, that's when you're talking about different chunks of charges. If an electron can emit 9 electric field lines, we don't have a different electron that emits 18 field lines. That's just 2 electrons as a chunk, so don't confuse. Here we're just assuming that we have individual electrons. So I'll go back. I'm gonna say that 1 Q corresponds to 9 electric field lines, okay? We have 3 plus Qs and 2 minus Qs. I'm gonna enclose them. I drew this region in a way that it crosses all the arrows that are not connected to the charges. Why? Look, can an arrow stop in the middle like this? So this arrow isn't exiting the region? No, right? It will keep going and eventually exit the region. And that's why I had to draw the region in a way to cross all the arrows, okay? Alright, so let's count the numbers of lines going in and out. These lines are going out, and these lines are going in. We have 14 lines going out, you can count that, and 5 lines going in. So this is 9 lines going out in total. Now, let's see what the total charge is. 3 plus Qs and 2 minus Qs, so 1 plus Q in total. Look, we have 9 lines going out in total and 1 Q in total. Perfectly equivalent. This was what Maxwell proposed. He showed that electric field lines do exist, and they can tell us how many charges are in there. So we got up till here now, and you know what? What Maxwell actually did was apply Gauss's flux theorem to electromagnetism. He didn't explicitly mention that he had applied Gauss's flux theorem in his papers, so he might have discovered it independently. But even if he didn't derive it himself, but instead applied the existing Gauss's flux theorem, the act of taking that mathematical knowledge and effectively using it is still an impressive accomplishment. Okay, so Maxwell was already quite satisfied with the investigation he has made so far. He was able to derive this integral expression to study the electric field lines, but he went a bit further. Say the electric field line was going in the x direction, that means we're talking about the dy dz area, which its normal vector is in the x direction as well, right? We could put a d over dx inside and in exchange add dx to integrate it back. So nothing's changed in overall, so there's no problem with doing that, right? Similarly, if the electric field line is going in the y direction, we're doing dot product with the dx dz area, which its normal vector is in the y direction as well. We could do the same thing to it. And also for the z direction case. This means we can generalize this as the divergence of the electric field integrated over a volume. Make sense? By the way, this also happened to be Gauss's divergence theorem. Take d over dv on both sides, and we'll arrive at this expression. Rho is the volume charge density. It looks much nicer. This is Maxwell's first equation. Applause. A beautiful equation that describes charges and their electric field lines. And this is also called Gauss's law, named after the German mathematician Carl Friedrich Gauss. You now see the reason why people named it this way. I admire Gauss a lot, but let's give Maxwell the credit at least in this video. When Michael Faraday heard the news that a young physicist had come up with an equation to mathematically formulate his idea, he wrote a letter of gratitude. He must have been excited to receive the letter. So this was one of the 4 Maxwell's equations, and this was the first equation to describe the behavior of the electric field mathematically. If you like this video, please like and subscribe to our channel. It really motivates me. Thanks a lot.